Hi, welcome to EE16B. My name is Sid,
And I'm Salvan.
and today we're going to do observers. Before we get started, we're sorry that we can't do all the topics that we mentioned. These videos usually take a long while to make, and so far the videos have taken 5 hours each, and we're kind of out of time too. So, sorry. So, we're going to do observers today. On that note, observers. So, Savan, how would you describe an observer, like just intuitively?
Well, it's a system that we make that allows us to estimate the current state of the system and the past states of the system.
Exactly. So, let me put it this way. Say you have an input. I'm going to work in discrete time because it's easier to visualize. So, I have an input, U of n. It goes into this some black box system that I have no idea of, like the mechanics inside, and I get the output y of n. Now, I know that this system has a state transition matrix A, an input matrix B, and an output matrix C. So I don't know anything inside of this, but I have a reasonable model for the system. So you're given this black box system. I'm going to model it as follows. X of n plus 1 is equal to A x of n plus B u of n, and y of n is equal to C x of n. So the point of this is that we know a model for this system, but we don't have access to these state variables x. So we'd like for a way to estimate it. So, Savan, how are we going to do that?
That's where observers come in, right?
Exactly.
But one question, Sid. So we know that we have an X vectors and we have an A state transition matrix.
Mm-hmm.
Do we necessarily know the size of these matrices when we design these systems?
So, good question, Savan. That's where physical intuition comes in. So, as a part of constructing this model, like where we use our state vectors x and a, a part of a model is the dimensionality of A, X, B, and C, and so on and so forth. That's when you have to use your physics knowledge or your circuits knowledge to try and build up this model. Cool?
Sounds good.
All right. So we're now going to construct an observer. We're going to construct a pretend system, but not exactly pretend, and we're going to call our state vectors to be x hat. So we're going to say x hat of n plus 1 is equal to A x hat of n plus B u of n. Note that this is the same u because we have access to it right here. And here's where we're going to do something a little different. We're also going to add some matrix times y hat of n minus y of n, where y hat of n is simply C x hat of n.
So, Sid, where do these A and B matrices come from? If we don't know the original A and B matrices, how do we get the ones for the estimated system?
But we do. That's part of the model. So this is where, again, we use our prior assumptions in making the system. The only thing we really don't have access to are the state variables x.
Okay, so we know A from our model.
Exactly.
Okay.
Which is why we can use them in this system. Now, the whole point of constructing this other system is that in this case, it's not really, let me start that again. It's not really a black box system anymore. So this delays by 1. I get x hat of n. This goes back to A, comes back to a plus. And then you have B. You have a U, and then you also have something that comes out here. That's like, you pass this through C, you get y hat of n, and then you take this whole thing and this whole thing, you subtract them, and you pass it back into the original system. The difference is, the reason why we do this is, in this case, for this system, we actually have access to these x hat of n's. So if you construct this well, instead of trying to find the x hat in this system, we can simply use the x hat instead of using the x in this system, we can simply use the x hat in this system. Sound good?
Great.
Cool. Okay, so why are we looking at y hat of n minus y of n? Well, by a model, we know that y hat of n is equal to c x hat of n, and y of n is equal to c x of n. So y hat of n minus yn is equal to c x hat of n minus c x of n, which is equal to c of x hat of n minus x of n. So Samad, what's a good thing that we can call this? Or what does this mean?
Well, if x hat is our estimation, right, of x, so if we have a good estimation of x, then presumably that would be 0, right?
Exactly. So we're going to define this to be our error term, e of n, and we're going to try and get this error to go to 0. So connecting it back to this diagram, this would be L times C times E of n. And we're going to try and pick an, oh, I forgot to put an L here. I'll put that right now. Actually, it should be right here. Sorry about that. Erase. Okay, L. So the reason why there's an L over here is we can actually choose the values of L so that this error term goes to 0. This is something that you have control over and something that is a design objective. Cool. So going back to this, from the last slide, we have our estimate to be estimate system or observer system to be x hat of n is equal to a x hat of n plus b u of n plus lc times e of n, and a y of n hat of n is equal to c x hat of n. Cool?
Cool.
So let's try and get everything in terms of e of n, because we want to try and get the error to 0, so might as well localize to that error. So if you remember, the true system that we have, but we're pretending to have access to, but we don't really have access to, is this. So I'm going to do some algebra voodoo and conclude that this is true, where all I've really done is take this term to this side of the equation. Now that I've done that, I'm just going to substitute this instead of this. You'll see why we're going to do that pretty soon. Sam, do you want to work out the rest of the algebra for us?
Sure.
Cool.
Okay. So
I like putting him on the spot.
So you have x hat of n plus 1 equals a x hat of n plus, putting that in, you have x of n plus 1 minus a x of n, right? So if we move...
There's also this term?
Oh, right.
Yeah, that was my bad.
LC, you're right.
Yeah.
E of n. Right. So basically we can push this into a bunch of error terms, right?
Yeah.
So if I were to move this x of n to this side and then, combine terms here, I should have a bunch of error terms left over.
Exactly. Just to draw it out, this term, you're going to combine these two terms together.
Exactly. So moving these over, x hat of n plus 1. Sorry, my handwriting is bad.
He's in the right side of the screen, and it's kind of hard to write from that direction.
Yeah, I have to be...
Yeah.
Anyways. So x hat of n plus 1 minus x of n plus 1 equals a times the quantity x hat of n minus x of n plus LC E of n.
And there's a bracket.
Yeah.
Cool.
So here we end up having E of n plus 1 equals A E of n plus LC E of n, right? So finally E of n plus 1 equals A plus LC times E of n.
So just one thing to note, whenever you see this L right here, I'm just going to change colors for this case. Whenever you see this L, sometimes you see people do minus LC times EFN. Sometimes you see people do plus. These are identical. The only difference is that whatever value you get for L in this case, you get a negation in this case. That's the only difference. It's just two different conventions.
Cool.
Cool. So looking at this system, the one right over here, we see that we've basically constructed a transition model for our error term. So one thing that we didn't really mention is when we're constructing this estimate system, we also have to initialize it. So we have to set x hat of 0 is equal to something, right? And we could start off with a really bad error, but the point of constructing an observer system is that as this propagates, as you propagate through time, your error converges to 0.
Sounds good.
So if you're familiar with like iterative methods or gradient descent or stuff like that, it is kind of like that. We're trying to get our error term to go to 0 as time goes by. Cool. So from the last slide, we have a model that looks like this. In the continuous time case, this simply looks like this. You can go through the derivation. It's almost identical. It is identical, I believe. The only difference is the difference comes in the design, which we'll elaborate as we get there. OK, so Savin, if you want, in a discrete time case, if you want an error term to go to 0 as time goes by, what does that tell you about this system?
Well, for the error to go to 0 eventually, well, we want the system to be stable, right?
Exactly.
So if we start off with some error, that it eventually decays rather than, you know, blows up.
Mm-hmm. So why might not we try and find the smallest, why can't we just say like the eigenvalue is, oh. Should we keep that in? We should keep that in. Okay.
Let there be light.
Let there be light. So Savin, why can't we, if we have this matrix, why can't we just set the eigenvalues to 0 in a discrete time case? And like have go to, like the error go to 0 like right away?
Well, I mean, in a physical system, you can't really do that. Like, you have constraints on the system. And although we model it like as distinct time steps, there's also things happening in the middle. Mm-hmm. And there's, if you have it immediately decay to 0, you could, I mean, in a physical system, you could have oscillatory behavior. There's a lot of things that happen that are really bad if you make it decay too fast.
Yeah. So think of a circuit, for example, and you're trying to control the circuit, and you tell it to, like, in the continuous time case, having the error go to 0 right away is equivalent to setting these eigenvalues at negative infinity. The real part of the eigenvalues are negative infinity. And what that means is you need an insane amount of like energy and power and current to like, bam, set it to 0 right away, which is not possible.
That's true.
Yeah.
And in addition, it also is highly impractical, right? You have parasitic things that you don't account for, second order effects. Yeah.
Yeah. So this is where the design component comes into it. Usually when we pick this L, we pick these L's to be within our system constraints that still gives us reasonable results, which is what we usually do optimization for, which we'll get more into in the linear algebra part of the course.
Yeah, and we'll talk, I guess you'll do your own optimization when you work on the final project.
Yeah. Cool. So, Savin, quick question. If A is, give me two numbers. Give me a number.
2.
Give me a number greater than 20.
42.
42. If A is a 42 by 42 matrix, C is going to, how many columns can you have in C?
How many columns can I have in C? It should be 42, right?
Exactly. So how many outputs do you want? Say I have 3 outputs. What should I put over here?
Then 3 outputs means that it should be 3.
Cool. What does that tell you about the dimension of L?
Well, L would have to be the, transpose dimensions, right?
Exactly. So whenever you're trying to figure out the dimensions of this L, look at your A and C, because since we're doing A plus LC or A minus LC, we want L times C to be a 42 by 42 matrix.
Right, for dimensionality to match.
Yeah. Cool. Let's get into a problem.
So just to confirm, then the L would be in that case, a 42 by 3 matrix, right?
Yeah.
Okay.
Sorry. Let's go into a problem. Random jump cut. This question refers to the eigenvalues in this question refers to the eigenvalues of the observer. Jump cut ended. So we have a continuous time system that says x hat is equal to this matrix A times x plus this matrix B times U, and output y is equal to this matrix C times x. So Salvin, I'll leave you to do controllability.
Cool. This is my favorite part. Great. So the controllability matrix, we write it as, I'm going to write it over here because it's easier. So C is B, A, B, A squared B, all the way to the A to the n minus 1B, right? And so n here is just a two-dimensional system. So C is just B, and then n is 2, so just AB. And we want to see if this is full rank, right? So
Why?
well, if it's full rank, then it's controllable, and then our input has the ability to, independently change both state space variables.
Basically, the range of the controllability matrix is our state space. So if you have rank n, it means that range covers all state space vectors.
Cool. Yeah. So B, 0, 1, multiply AB, you end up with 1, negative 1. And we can see that this is full rank.
Yeah. Cool. Now I'll do observability. So the observability matrix, which I think people call O, I guess it makes sense, but it confuses me with 0 sometimes. I'm going to call OB. Ob. So ob is equal to C, CA, CA squared, and so on. But all the way to CA of n minus 1, which again, as Salvin said, A is just equal to 2, so this is just C times CA. So the reason why we construct this observability matrix like this is if you look at, if you assume you had no input, for example, if you had no input at all, just because it's easy to see, you can have x of 0 times C, CA is equal to y of 0 and y of 1. What observability basically boils down to is if you have a set of initial conditions, if you have a set of time points, can you uniquely determine the initial state, which, like the last example, comes down to the rank of this matrix.
Yeah, and if you can uniquely determine the initial state, that means you can also uniquely determine any of the subsequent states, right?
Yeah. Cool. Now that we've done that,
we should call this Bob.
Bob
matrix.
The Bob matrix. B-O-B. Didn't he make a song with Neil deGrasse Tyson about the world being flat? Or am I thinking of someone else?
Might be someone else.
Might be someone else. I think so. Anyway, never mind. So let's try and figure out what this observability matrix is.
Our Bob matrix.
Our Bob matrix, B-O-B. If you look at this upside down, it's a crying clown, which is relevant. Okay. Okay. So our C matrix is, I'm sorry, 0, 0. And now we need to find out what a CA matrix is. Let's do some 2 by 2 matrix multiplication.
I'm horrible at this.
Yeah, we actually had to cut some stuff because we spent too long on this. So it's not one of our proudest moments. So the first point would be 0, the second point would be 1, this would be 0, and this would be 0.
Cool.
So then putting this back in here, we get 0, 1, 0, 0. So Salvin, how many linearly independent columns do you have?
Well, we have 2 linearly independent columns, right?
Cool. And what's the dimension of our state space?
2.
So is it observable?
Should be.
Bingo. Awesome.
Hey.
So let's try and construct our observer. So erasing this.
Just a note, remember that your observability and controllability matrices don't have to be square.
Yeah.
we generally like to make them square just because it makes, proofs and stuff easier with C and C inverse, but they don't have to be.
Sounds good. Which is why in this case, it's if you see something like this, you look at the dimension of, basically this dimension of the space spanned by these two vectors should be equal to the dimension of this.
Right.
Cool. I'm going to leave the crying Bob the clown, just right there.
Great. So it is controllable and it is observable.
There's a happy Bob here. Cool. Okay, moving on. So we're going to try, when we try and construct the observer matrix and we want, don't look at me like that, and we want the error to go to 0, we're basically looking at a matrix of the form E of n plus 1 is equal to A plus LC times E of n. Saban, what's the dimension of L?
Well, if C is a 2 by 2, then L should also be a 2 by 2.
Sounds good to me. So we have, we're going to say L is equal to L1, L2, L3, L4. I'm beginning to regret putting this problem now that they're 4 variables. So A plus LC. Oh,
Hey Sid, why do we care if it's observable to place eigenvalues?
Right. So if it is similar to the case of controllability, we are not guaranteed to be able to place the eigenvalues anywhere that we want if it is not observable. So observability basically guarantees that we can place all the eigenvalues anywhere that we want.
Cool.
Cool. So this whole mess is, oh, I don't want to do this. 0, 1, minus 1, minus 1, plus L1, L2, L3, L4.
Don't worry, our C matrix is pretty friendly.
1, 0, 0, 0. I guess. Do you want to do it?
It's all you, buddy.
Dang it. Plus, this would be L1. That would be 0. That would be L3. That would be 0. Does that look about right?
That's not bad.
Yeah, actually not that bad.
Great.
So, which is equal to L1, 1, L3 minus 1, minus 1. That looks like a 6. So in order to place the eigenvalues, we're going to look at the characteristic equation. Yeah.
Yeah?
Yeah. So, so lambda I minus A minus LC.
A plus LC, right?
A plus LC, sorry. This is me getting confused with the other convention. This whole thing is equal to 0. So, oh my god. So that becomes the determinant of lambda minus L1, 1, L3 minus 1, lambda plus 1. The determinant of this is equal to 0, which becomes lambda plus 1, lambda minus L1.
This should be negative.
Should be negative?
Yeah, see, this is positive, so it becomes negative.
Cool, thank you. Then would this be a negative too? Yeah, this would be a plus then. Yeah, that looks about right. Okay, so A plus LC is this thing. So minus L1, minus 1.
Oh, this should be negative, actually. This is.
Yeah, this should be a negative.
Yeah.
Yep.
Cool. Math is hard, man.
This will also be a plus 1. You minus
yeah,
plus.
You did.
Okay.
Okay, cool.
Cool. That 1 minus L3, right?
I'm bad at math.
1 minus L3.
Plus
1 minus L3.
Plus 1 minus L3.
Yeah, because it's like minus the product of these two.
Yeah, you're right.
Cool.
Equals 0.
Math with Sid and Savan. That's why we're the banter boys and not the math boys.
True.
Jeez. I regret saying that. So we have lambda squared minus L1 plus 1 lambda minus L1 plus 1 minus L3 is equal to 0. I'm going to erase this side, but I'm still going to keep the upside down crying clown. Salvin, did you see any clowns in Berkeley?
I did actually.
Really, where?
4 in the morning on Durant and Telegraph.
No way!
It was really creepy. I thought I was losing my mind. Anyways.
That's crazy. Okay, so writing it out here again, we have lambda squared plus 1 minus L1, lambda plus this whole mess, 1 minus L1 minus L3 is equal to 0. So if you want our eigenvalues to be placed at -2 and -2, we want a characteristic polynomial to look like this, which is lambda squared plus 2 lambda, sorry, 4 lambda plus 4 is equal to 0. So matching coefficients, this tells us that L1 is equal to...
Well, 1 minus L1 is 4, so L1 is -3.
-3, thank you. And this tells us that, so this is 1 plus 3 minus L3, which is 4 minus L3, which tells us that L3 is equal to
0.
0. What about L1? What about L2 and L4?
Well, we can do whatever we want with them, right? Whatever's most convenient when we're building the system.
Exactly. That's pretty much because these ones are set to 0.
Yeah.
This is basically equivalent to something that looks like this. But here we have 2 outputs. This is like if you have an output vector of 2 vectors, but this was just forced to set to 0 all the time.
Seems a little redundant, but anyways.
Yeah. Anyway. We use the 2x2 matrix to show that the observability matrix doesn't have to be a square.
Yes.
Cool. So, now that we have that, we have constructed an observer for our system.
Nice.
Cool. Now we'll do one more problem, and this time Salvan will write. Now that the jump cut is done, we're back in the present, which is your past. Okay. Bob is necessary. We need to put Bob in here. Happy Bob.
Bob, the traumatized clown. Anyways. Oh boy. All right.
That's observability matrix. So we can, is the rank of this equal to our dimension of a state space? Never mind. Okay. Bye, Bob. You know what? You're welcome. Sal, do you want to do the problem? Okay. Good luck for your exam.
Great. So here we're designing the observer eigenvalues to be at -2.
Mm-hmm.
So we're trying to place L1 and L2. We're not trying to place the eigenvalues of the overall system, just the observer eigenvalues.
As verified by a jump cut.
By jump cut.
By jump cut. Praise Bob.
Okay, so this is our C matrix, this is our A matrix, and this is our B matrix, right?
Cool. Wait, so is this controllable? I mean, observable?
Well, let's check.
Let's construct Bob.
Our
Bob V2.
So this should just be
C.
C,
Yeah.
right, C, and then AC.
Nope.
Oh, sorry, CA, my bad. CA, CA squared, all the way to CA n minus 1.
Mm-hmm.
And here n, we decided to make this difficult and have more algebra, and so it is dimension 3.
Praise be Bob.
So C, we have CA, and then CA squared.
Yeah.
And then let me make this smaller.
Mm-hmm.
Great. So C is just 1, 0, 0.
Mm-hmm.
All right. CA, I can do this. 1, 0, 0. CA equals 1, 0, 0 times -1, 1, 0, -1, 0, 1, 2, 0, 0.
It'll just be the top row.
You are correct. It is just the top row.
Cool.
Cool.
Now you get to calculate A squared.
Oh, so much fun.
This looks annoying. Oh, don't forget the minus.
Yes, thank you. Squared.
Bob.
So calculating CA squared, this can be reduced to -1, 1, 0 times the original A matrix, because this is CA. 1, 0, -1, 0, 1, 2, 0, 0.
So this is the second row minus the first row.
Yeah. So this. So the first one is what? -1.
It's the second row minus the first row.
Yeah, I know.
Just do it.
-2, -1, 1.
No.
Did I do that wrong?
This minus this. This -1 minus 1. It should be
Oh, this is a 0.
Okay.
I can't do algebra.
This minus 1. Okay, you good.
Yeah, I just did the first one wrong.
Cool.
Cool. All right, so
He has NSF due soon. He hasn't been sleeping well.
no, stress, man. It's bad for you.
That's
All right.
why we like Bob. Cool.
Super.
So
So
is it observable?
I don't know, Sid. Is it?
Yes.
How can you tell?
Because in this case, there's nothing in these two rows that could reach this. There's nothing in.
So you can cancel out this one with this.
Yeah, you can do row reduction.
Row reduction wise, it works out.
Yeah. Yep.
Cool.
Cool.
All right. So now for a, we can write our error as E of, or E, this is continuous time, right? So E dot
Yeah.
equals A plus LC times E, right?
Cool. Do you want to erase all this stuff?
Yeah, let's do it.
Cool. Do you want to name the clown you saw, Bob?
That was freaky.
Bob freaked you out?
Yeah.
I feel so bad for anyone named Bob right now.
We know a Bob.
We know a Bob.
Yes, 16 ATA Bob.
We should just call him a clown without any context.
He is a clown. It's okay. In a good way.
Thanks for making that clear.
Good clown. I really hope he doesn't watch this video. All right, so we have A plus LC. So A plus LC equals -1, 1, 0, -1, 0, 1, 2, 0, 0, plus L.
What's the dimension of L?
Oh, L is, the transverse dimensions of C, right? So L is this.
L1, L2, L3.
A. And then
L.
C is 1, 0, 0.
Cool. An embarrassing amount of time later, we figured out how to do this multiplication.
Yeah, we're algebra is something we don't do very much anymore.
I think we're just tired.
Sid works in the theory world where they don't use actual numbers. And I worked in the practical world where we never work with any numbers.
And we both live in a world where we use MATLAB.
True. L1, L2, L3, 0, 0, 0, 0, 0, 0, which is L1 minus 1, 1, 0, L2 minus 1, 0, 1, L3 plus 2, 0, 0. Super. All right, so now we got to set all of these eigenvalues to -2, right?
Yeah. This shouldn't be, the determinant of this shouldn't be too hard, right?
I really hope so.
Well, you're doing it.
Okay, so the determinant of A minus lambda I should be 0 for the just find the eigenvalues. So A minus lambda I, the determinant of L1 minus 1 minus lambda, 1, 0, 1. Sid, I think you were wrong.
What?
The determinant of this is going to be a pain. We'll see.
We'll see.
Equals 0. All right. So we have
God.
So going down this column, times minus lambda. Here you have plus L3 plus 2. It's this one, and then this one zeroes out because of the 0 in the corner. Going up, this is a 0, this is a 0, and then the only one we have is plus minus lambda times L2 minus 1. Yeah. Right?
Do you want to double check on Wolfram Alpha?
I think we got this. I think we did this correctly.
Okay.
Pretty sure we did this correctly.
In case we did it wrong, we're sorry.
Yes. Okay. So here we end up with minus lambda cubed
Plus lambda squared times 1.
minus lambda squared.
I was going to say plus lambda squared times L1 minus 1. Or you can do 1 minus L1.
Whatever. Because we have to do component matching at the end anyways.
Yeah.
Plus lambda squared L1 plus, so we're because we need to do component matching, we should just keep them all together.
Cool. Yeah, that works.
Yes.
And now
yes.
we want the eigenvalues to be at -2, -2, -2. So which means you're matching to a polynomial that's lambda plus 2 the whole square cubed.
Yes. So we're matching to, yeah, so we should actually negate all of this anyways.
Doesn't matter.
Yeah, whatever.
Yeah, we can keep that in mind later.
So lambda plus 3,
2.
2, lambda plus 2.
2.
Sorry. Replacing them all at 2 cubed, which is lambda cubed plus
8.
8. Is it 8 lambda?
No, just 8. That's a constant term.
No, plus 2 cubed. You're going to have some, you have like middle terms too.
Yeah, but I was just the ones that we know first.
Oh.
Plus
Okay.
8.
I was just going to do the binomial theorem. Anyways, plus
3 lambda squared 2. So 6 lambda squared. Yeah, you're fine.
Okay, I was doing it correctly. Sid, come on.
I'm sorry. Yeah, sounds good. Okay, so what does that tell you about L3 plus 2?
Great. Yeah, L3. Can we just, I'm going to erase this part so
Okay.
we have space.
And, yeah.
Cubic functions are wonderful. They're kind of a pain in the ass, but whatever.
I don't think we can mention that. We're going to keep it in.
Anyways, so we want to, let's just negate this so that our initial coefficients are all the same. So we have lambda cubed plus lambda squared minus L1 lambda squared.
Yeah.
Squared.
Plus lambda L2 minus 1.
Plus lambda L2 minus 1.
Minus 2. Minus 2 plus L3 in brackets, parentheses. Yeah.
Great.
Cool.
And then we want to match it to lambda cubed plus 6 lambda plus, lambda squared plus 6 lambda plus 8 equals 0.
Cool.
Great. So we want this whole thing to be equal to 8. So we have minus L3 plus 2 equals 8. And therefore, L3 is negative 10.
Just 6. 6 plus 2 is 8. Oh, right. Sorry. My bad. Yep.
This is why we have the two of us together. And then matching this lambda term, we have L2 minus 1 equals 6. Therefore, L2 is 7. Right? Yeah? Okay. And then we have 1 minus L1 equals 6. So L1 is equal to
Negative
5.
Cool.
Awesome. So our L looks like negative 5, 7, negative 10.
Cool. That was a lot of work.
Cool.
Bob is happy.
And Bob is also prepared to ace this 16B midterm on
And eat
Tuesday.
your souls. Okay.
Thanks,
Bye,
everyone, and good luck.